So our project is called Gauss Rifle or Linear Accelerator. So our purpose was to study how the magnetic force of neodymium magnets accelerated the steel balls. And we tested a couple different things. We wanted to test the distance between each set of magnets. Our sets had 2 magnets in each of them, for the most part. Another thing we wanted to test is the number of sets, how that affected the final velocity. That's what our data was. That was the final velocity of the last ball shooting off. And we also wanted to test how changing the number of magnets in each set affected the final velocity.
And then we also did an experiment while we tested the magnetic force versus the separation distance by using like a B-field sensor. So this is the background. So the magnets that we used were rare earth metals, so they're really strong, and they're called neodymium magnets. And so they're used for like a lot of things, like electric guitar pickups, which we did in class earlier this semester, headphones and loudspeakers, then also electric cars and MRIs. And so this Gauss rifle invention idea was made up by Carl Friedrich Gauss in the early 1800s. And he actually has his own unit, and so 1 Gauss is equal to 1 times 10 to the negative 14 Teslas.
This is a measurement of magnetic.
You can correct that later. It's not the right relationship. But it is a measure of magnetic field.
Oh, oops.
Alright, so this is our setup here. We set up the most exciting one. We found that the 4 sets of magnets, which was the fastest velocity, ended up right around 4.5 meters per second. Right now I just put this at a random angle, but we had was it 10 degrees or so?
Yeah.
Yeah. So it's to the end. So what's going to happen is this ball is going to go down the ramp, and it's going to be accelerated into these magnets, and the momentum that it has is going to be transferred to this ball. This ball is going to shoot off, and the reason we have 2 is because the magnetic force on the first one is too strong for this ball to accelerate out of the magnetic field.
Also, these balls are called grounded, so they need energy to be transferred into them to allow them to move. So that's what this ball is doing. It's transferring its kinetic energy and allowing this end ball to break off, and then the same occurrence happens.
Almost like the Newton's cradle. Then it's just going to keep accelerating through the 4 steps.
Wait, should we call the nurse?
I think we should be alright.
Okay.
It might go through my hand, but that's okay. What?
Oh, very exciting. Alright, let me increase the angle. I don't think this is very big.
That's not what it's supposed to do.
No,
that's
redo.
not what it's supposed to do. Alright, here we go.
Is there something interfering?
I think so. Good, alright.
Mm-hmm.
There it goes.
Holy cow.
Yeah.
So yeah, sometimes we have tape taping it down, so sometimes the tape will get in the way or there'll be another interference. But
Alright. So our equipment, we have 10 magnets, I think, 22 walls, and then this wooden setup. Here's a picture of the setup there. Yeah, so those are the things we tested. We tested the separation distance, the number of sets, and the number of magnets in a single set.
so these are some slow motion videos that can show you what was happening in slow motion. So this is ours, and this is one that I found offline that's really, really slow. It'll work.
Is the video file in the same folder? Is it embedded somewhere?
Yeah, I embedded it into the presentation. Sure.
Yeah, there are a lot of these projects on YouTube. Yeah, it's,
See if I can find them. well, let's do this one. So that's like what you saw.
What's happening is this first ball is going to go into this one and it shoots off. It's a quick chain reaction.
And so what we studied was the final velocity of the last ball. So this is our data. So our first graph was the final velocity.
YouTube.
So our first graph was the final velocity of the last ball versus the number of magnets per set for one set. And so we found it have a curved fit and
so what we think is happening, we thought that, initially we thought that the more magnets we added, the stronger the field would be and the faster it would accelerate. But there's, every time it hits a new magnet, there's just some energy lost in there, so it ends up slowing down at the end the more magnets we add.
And then this one was really interesting because it had, so it was the final velocity versus the number of sets of magnets. And so we thought that as we increased the number of sets of magnets, the final velocity would just steadily increase. But in fact, it increased and then started to decrease again. And so we looked online and everything for why this was happening, and we found some stuff through magnetism and what Gauss discovered and everything, but we didn't really know how to go about it because a lot of the things we hadn't studied yet. And so that's something that we would like to go into and study more if we had that knowledge, so maybe next time. And then this is the final velocity versus the separation of sets of magnets.
So when we were trying to come up with a hypothesis for this one, we were going back and forth between deciding whether decreasing the separation distance would increase the final velocity, because the field would be a lot stronger the closer you get. So the acceleration would be a lot higher, but it would only accelerate for a shorter amount of time. So we thought that might result in a really high final velocity. But we're also thought if we made it really far apart, it would accelerate the entire time, but it would be slower because the field wouldn't be as strong further away, but it would accelerate for a longer amount of time. And so we just picked one. We picked that the longer separation is, the faster the final velocity will be. But it ended up being right in between those two, having medium between decreasing the distance, the final velocity increase, and also increasing the distance, the final velocity increase.
And so this is the last thing that we tested. So we tested the magnetic field versus the distance, like the separation from the B field sensor. And so it's an inverse relationship of when we increase the separation, the magnetic field decreases. And so this is kind of like what we observed. So what's happening is the transfer of kinetic energy. So it goes from the moving ball to the magnet to the stationary ball that's at a ground state. And so it's kind of like somebody playing pool. So if they're shooting the cue ball at two balls, they shoot it through the first ball, which stays still, and then the second ball will travel with the energy. And so the second ball moves towards the second magnet and picks up the velocity, and then the cycle continues for however many sets of magnets you have. And
yeah, so our only most of our hypotheses were correct except for
separation.
Yeah, separation. There was just that medium between the two that we hadn't thought of. We picked one. It was both. Yeah. Right.
It also, we were trying to come up with something that would give us infinite energy, and so we were playing with this a lot, and probably more than we should have. But we wanted to create like ramps on both sides or something in order for the ball to transfer back and then start the reaction again.
And there'd be some energy lost between each one, so it obviously wouldn't go on forever. But
yeah, but then we thought of like a circular track and see if that would work. But the problem with that is that it would have, when it comes around again, the initial ball, there would be 2 ground-stated balls rather than the one, and that would not allow the kinetic energy to completely transfer through it. So any questions?
Did you guys look at all of the conservation of momentum in between each ball and the?
no, we just focused on the last one.
What we were doing is we didn't have like, we used a high-speed camera and we used Logger Pro to plot the points, and so it wasn't very accurate, and that's why we had so much discrepancy in our graphs. And so we started off trying to do that, but it just looked a mess and everything. So we were trying to think of a better way, but then we ended up just focusing on the final velocity and.
So on here we marked every 2 centimeters, and that's how we did the graph on Logger Pro to gain speed.
I thought you guys had set that up on a low friction cart and noticed that the cart went the other direction. Didn't you do that really early on?
We were doing that. We were just playing around, and so we set this whole thing up on a cart, and we had a little bit lighter setup where we had to switch. So when we shot it out, the ball shot out this way, but the cart went backwards
that's so
because
cool.
of conservation momentum. Yeah, it didn't go back very fast. That's one thing. For more time.
Yeah, there's a lot of things that we wish we could have done with this lab, and so we did a lot of them, but we wanted to do a lot more. But the time constriction was kind of against us.
I just wanted to say that I love the term ground state for the 2 spheres or 1 sphere in before and after cases, that it's right next to the magnet because it's the lowest energy, because it's the most tightly bound. It super ties into our discussion of atoms just yesterday.
Yeah, and like this lab, although it seems kind of an easy concept, I took like a lot of time researching about it and how everything works, because I had no idea. We both had like no idea how it worked. Like we thought it was more of like the magnetism working in it, and so a lot of the time we spent researching, and then we would have used that time to, if we had known all of that stuff, we could have done like more experiments. But
Next time.
exactly.
So if you could really succinctly tell me why a circular track that's repeating itself won't work in terms of energy. What is it, the main issue?
Well, the main issue is that when the ball is going to come back around, it's going to hit this, and it's just, this ball isn't going to go because it's too tied to this magnet. And I can show you here, like when we set up the ramp, I'll just push it. Like, it doesn't go because this ball is too close to this one, but we're going to put another ball here.
So it will work for like a singular rotation, but then the second rotation won't work because the balls are out of line.
It shoots out, but the one didn't work because
It's too highly tied to the magnet.
It would not reduce its energy to leave, so
Exactly.
it doesn't.
It's happy there.
It's like dominoes.
Exactly.
One time around is all you get. Thanks, guys.
So our project is called Gauss Rifle or Linear Accelerator. So our purpose was to study how the magnetic force of neodymium magnets accelerated the steel balls. And we tested a couple different things. We wanted to test the distance between each set of magnets. Our sets had 2 magnets in each of them, for the most part. Another thing we wanted to test is the number of sets, how that affects. We set up the most exciting one. We found that the 4 sets of magnets, which was the fastest velocity, ended up right around 4.5 meters per second. Right now, I just put this at a random angle, but we had like, was it 10 degrees or so?
Yeah.
Yeah. So just at the end. So what's going to happen is this ball is going to go down the ramp, and it's going to be accelerated into these magnets, and the momentum.
So this is the background. So the magnets that we used were rare earth metals, so they're really strong, and they're called neodymium magnets. And so they're used for like a lot of things, like electric guitar pickups, which we did in class earlier this semester, headphones and loudspeakers, then also electric cars and MRIs. And so this Gauss rifle,
The final velocity, that's what our data was, that was the final velocity of the last ball shooting off. And we also wanted to test how changing the number of magnets in each set affected the final velocity.
and then we also did an experiment while we tested the magnetic force versus the separation distance by using like a B field sensor. Like idea was made up by Carl Friedrich Gauss in the early 1800s, and he actually has his own unit, and so 1 Gauss is equal to 1 times 10 to the negative 14 teslas.
This is a measurement of magnetic.
You can correct that later. It's not the right relationship. But it is a measure of magnetic field.
Oh, oops.
So this is our setup here.